we've seen so far that big O, and I'll say big O dot, just to say that it has some argument here, but I won't specify the argument. So big O is like less than or equal to. Big omega is like greater than or equal to. And those are useful, but almost exclusively in this class, what we're going to use is something called big theta. So big theta lets us say something with much more precision than big O and big omega, because big theta corresponds roughly to equals. So big theta ends up being a pretty useful thing for us when we're trying to be exact when we're talking about something. So if you'd like, you can think of big O as something like this. So let me draw my t of n function here. So there's t of n. Here's my other function. I'll call this my g of n, my reference function. And so here, this is a situation where t of n is big O of g of n. Right? If I zoom out far enough, and if I squint so I can't read the numbers, eventually I'll see that g of n is always bigger than t of n, right? So we have this less than or equal to relationship. We can also draw something that corresponds roughly to a big omega. And so we could do something like this. We could say, here's my t of n. There's t of n. And here's my g of n, my reference, my g of n. Here I would say t of n is big omega of g of n. Right? Because t of n, if you zoom out far enough, t of n is always going to be larger than g of n. But now I'd like to talk about a concept that's a little bit more targeted, right? So all these allow us to say is that t of n grows faster than g of n. So for example, in the big omega, t of n grows faster than g of n, but we don't have any information about how much faster. And similar with big O, g of n is faster than t of n, but we don't know how much faster. So what we'd like to do is we'd like to come up with a way of saying, here's exactly how fast t of n grows. And we'll do that with big theta. Okay, so here's the idea of big theta. So I want to draw a function, t of n, that is big theta of something that I'll call g of n. Right, so if this is my t of n, oh boy, hang on. Back up, there we go, okay. Eraser off. If this is my t of n, here's t of n. Then if t of n is big theta of g of n, then that means I can sandwich t of n in between two scaled copies of g of n. Okay, so that means I might be able to draw something like this. Here's g of n. And here's g of n scaled up. So I'll call this C1 g of n. And maybe just for completeness, I'll call this C2 g of n. Or yeah, C2 is fine. Okay. And so what do we have? Well, we have that t of n, if we go out far enough, if we zoom out far enough, t of n is always going to be in between these two scaled copies of the same function, g of n. Okay, so again, just like with big omega, I won't write out the full definition in words, but in math, it looks like this. I say t of n is, actually I've already got that written right there. So t of n is big theta of g of n. And so this is if there exist constants c1 greater than 0 and c2 greater than 0, and a big N greater than 0, same as before, such that t of n is less than or equal to c1 g of n, and greater than or equal to c2 g of n, for all little n greater than big N, right? And so this is the if I zoom out far enough, and this is the if I squint so I can't read the numbers, right? So this is the part that says if I pick my constants right, I can make it so that t of n always stays in between g of n, two scaled copies of g of n. All right, so here's a question, right? Now suppose I have the following, and I'll leave the definition right here. Suppose I have this. So suppose I have some function f of n, and that this is big theta of g of n. Big theta of g of n. What can I say about big O and big omega? So is f of n big O of g of n? And I'll say is f of n big omega of g of n? Okay, think about that for a second. Feel free to reference the definition above. Pause if you like. The answer to this is yes. To both questions is yes. Okay, so why is that? Well, what does big O mean? Big O, and I'll use red for this. So big O means that there exists a C1 greater than 0, and there exists an n greater than 0, such that this inequality holds. Okay, for all n greater than n. So the fact that we have big theta already established, right, that this is already true, the fact that we already have big theta established means that big O is satisfied automatically, right? So f of n is big O of g of n. All right, so what about omega? Well, the same exact thing holds. What does omega mean? It means that there exists a constant such that this inequality holds, right? So literally, big theta is exactly the intersection of big O and big omega. And so here's a fact. This is an important fact. And this is one way of writing it. There are a couple other ways of writing it that I can talk through. So this is a critical fact. Big O of f of n is exactly equal to the intersection between big theta of f of n is exactly equal to the intersection between big O of f of n, so intersect, and big omega of f of n. All right? And because of all the important dualities in Boolean algebra, this means the following. This means that if a function is big theta of f of n, then that function is big O of f of n and big omega of f of n, because of the connection between and intersection.